Human.
Oh god. You okay?
Professor Steve here, about to explain to you the concavity test. Dun dun dun. Alright, we're first going to start out with this function, x plus 2 quantity cubed. So, in order to take the derivative of this function, we first factored it out. And we got x to the third plus 6x squared plus 12x plus 8. Now, to find the first derivative. First derivative is 3x squared. This pencil is messed up. Plus 12x plus 12. You see, in order to have the concavity test, we need the second derivative.
True that.
And that would be, the second derivative is 6x plus 12. Now, in order to find the points needed for this concavity test, we set this function equal to 0, and what we end up getting, -2. And if Professor Brian could stop laughing, I could do this. Alright, now we set up our table of integrals. Our first interval will be negative infinity to negative 2, and our second interval will be negative 2 to infinity. Exactly. Now, we take these intervals, and we find a point, a number between these two numbers, and plug it in to the derivative. The second derivative, not the first derivative, the second derivative. And when we plug in, let's say -5, we end up getting a negative number. And this means that we will have a concave down. And then between these two numbers, say we plug in 1, we will end up getting a positive number. And that means we have a concave up. Now, since we have a sign change, we know we have a point of inflection. Exactly. So, we will take this number, -2, right here, and we will plug this number not to the derivative, but the original.
Preach it, Steve.
The original equation. Now, we get -2 plus 2 quantity cubed. Well, would you look at that? -2 plus 2 is 0. 0 cubed equals 0. So our point of inflection is -2, 0. Bang.
Oh,
Cut.
You want to cut it?
You stop this.
Wait. Ah! Professor Brian's coming in hot at you live. Boom, how did that line get there? I don't know. Let's say we take this function, e to the -x squared. Well, the first thing we want to do, you see, is derive that. We can do that quite easily. We simply take e to the -x squared because it stays the same, and derive the subfunction part to get -2x. I'm not sure if subfunction is a word, so don't quote me on that. Anyway, since this is our derivative of this, when we do the product rule, we will simply take this same thing for the first derivative part.
Don't forget the negative.
Oh, I don't just forget negatives. Professor Stevens. This is all that math that you don't need to know how to do.
Yeah, I do.
JK, there it is. Then fix it up nice and clean. What we're doing here is just pulling out things in common. And so we end up with this as our f double prime of x. And now, as Professor Stevens stated so nicely, we are working with the second derivative, which we have achieved. And so we're wondering, where does this equal 0? Well, that's never going to equal 0, so don't worry about that. But this inside, that might. And it just happens to at plus or minus the square root of 1/2. So these are critical numbers for our interval test. Our second derivative interval test. Note the difference between normal critical numbers and the first derivative. So, set our intervals. And you might want to use a calculator for this, because when plugging in ugly numbers, even though you're not plugging in this, you might get something gross in this function. So, what we found is that we had a plus, a minus, and a plus for our answers when we plugged in values between these intervals back into our second derivative, because we want to plug back into the derivative that we used to create this chart, not the original function. And then, from there, because, as Professor Stevens mentioned, because we have a sign change, we're going to use these as our x values for our points of inflection. So we have negative root 1/2, comma something, and positive root 1/2, comma something. And again, as Professor Stevens mentioned, we plug it back into the original. And what we got, and we had to use a calculator because this is a gross function, we got 0.607 both times. And so there, you see points of inflection.